Alright, so today we are looking at the Pythagorean theorem. So we have a picture of a right triangle here. That means it has a triangle with a right angle or a 90-degree angle. So that is right here in the corner. And then we have two sides of the triangle are going to be called legs. Those are both the sides that are right next to the right angle, and then the hypotenuse is going to be the side that is opposite from the right angle. So I always think of where is my right angle, draw a line across, and that's where the hypotenuse is. The hypotenuse is going to be using the letter C, and the legs we're going to use letters A and B, and we don't really know why yet, but we'll see why in just a minute. So we're going to have some questions to answer, and it asks us, for our questions, draw little squares inside of each big square to show area. So what that means is, like the example here, they knew that the side of this triangle was 3, so they made 3 rows of squares, and it's a square, so it means it's 3 by 3. So they filled it in with 3 by 3 squares, and they found the area, the total amount of space inside. There were 9 squares inside. They did the same for the side of the triangle that had 4, so 4 by 4, and the side that has 5 was 5 by 5, and they found all 3 areas of the squares. Now it's our turn to do step 3, which says to add the areas of the 2 legs together. So the legs are 3 and 4 because our right angle is in this corner, so this is our hypotenuse, C. Our legs are A and B, and it does not matter which one you want to call A and which one you want to call B. But the area of the first leg, where the number is 3, is 9 squares. The area inside the leg that was labeled 4 is 16 squares. And then it just asks us to add those two numbers together. So if I add 9 plus 16, I get 25. And now I'm supposed to answer the questions. It says, how does the sum of the 2 areas, so sum meaning I added them, of the legs compare to the area of the hypotenuse? So what it's asking is, how does this number 25 that we just wrote down compare to the number inside this large square over here, 25? So I'm going to write that they are equal. So when I added the 2 small squares, it was equal to the area of the hypotenuse. So it says, how is each side length related to the square on the same side? So how is 3 on the triangle related to the number 9 in the square next to 3? And how is 4 related to 16? And how is 5 related to the square by 5, 25? And I can tell from this pattern that it's 3 squared turns into 9. 4 squared turns into 16. And 5 squared turns into 25. Which makes sense because it's a square with the sides 3. So 3 squared would give you the answer for it, 9, 3 times 3. Then it says, how do you go from the area down to the side length? So how could I turn a 9 back into a 3? Well, that's what we talked about yesterday, doing the square root. The square root of 9 is 3. And we'll do it again. The square root of 16 would take you back to the side length 4. The square root of 25 would take you back to the side length of 5. So we turn the page and we've got 2 more problems that we were supposed to do the same thing. So if we want to, we can draw that this top square has the sides of 6 all around, and we could draw in all those little squares like it asked us to find the area, but I don't think I need to. I know that the area is just going to be 6 times 6, or 36, and I'm supposed to write that number over here in the first blank. My area for this square, all of the sides are 8, so I find my area length times width. 8 times 8 is 64, and I put that in the second blank. My biggest square, all the sides are 10, so to find my area I do 10 times 10, and I get 100. when I finish my equation with the blanks, 36 plus 64, that answer in my calculator is 100. So it asks me, again, how does the sum of the two areas of the legs, which are the small squares, compare to the area of the hypotenuse, which is the big square? And I'm going to say they are equal again. When I added the two small squares, it got the number that was in the big square. Then it says, how is each side length related to the square on the same side? Well, the same thing happened. 6 squared turned into 36, 8 squared turned into 64, and 10 squared turned into 100. If it asks me the next question, how do you go from the area back to a side length? Same as last time. To do the opposite, you do a square root and it turns it back into 6. Take your big number 64, do the square root, it turns back into the side 8. Square root of 100 turns it back into the side number 10. We've got another one. This smallest square has the area 5, so 5 times 5, that would be 25. Let me put that in the blank up here. My other square is 12 on every side, so 12 times 12 would be 144. My third square has 13 on every side. 13 times 13 is 169. And if I add my two numbers in my formula again, 144 plus 25, it also gives me 169. So how did those two squares relate to the big square? I'm going to say that the small plus the small, I should be more specific, the small square plus the small square equals the big square. How is each side length related to the square on the same side? Well, same thing. The side number 5, you squared it and you got the number for the area, 25. Took the number 12, square it, you get 144, this number on the inside of the square. 13 squared gave us 169. And to go backwards, we're practicing backwards of a square is a square root. So I do the square root of 169, get 13. Square root of 144 takes me back down to 12. And the square root of 25 takes me back down to 5. So I've done a couple examples like these now, and I think I'm starting to get the hang of the pattern. So on our last page, we get to predict. So we want to say, what would the area be on this side where it is 5? So 5, 5, 5, 5. It's going to be 25. 5 times 5. Put that in the blank. The square with sides of 6, I'm going to have to do 6 times 6, and I'm going to get 36. If we had to guess what we could do to get the question mark square area, to figure out what this is, I'm going to try the pattern that's worked so far. I'm going to do 25 plus 36, and I think that's probably going to be the number. That number would be a 61, so I'm pretty sure that's going to be a 61, and I'm pretty sure this is going to be 61 also, if we're following the pattern. Now it asks me to use the patterns we've seen to write a sentence. Complete the sentence below and use our diagram. If a triangle is a right triangle, then the area of the small squares added together is the area of the large square. The area of the small squares added together is the area of the large square. And I'm going to go ahead and label that this square in my picture that has A, I'm going to label that it has more sides called A. And if I wanted to know how to write the area inside there, it would be A squared, A times A, which means that the part in B, the square with B for all the sides, b times b, we can say that's b squared. And our largest one with c for all the sides, c times c, c squared. And what we said for the small squares added together makes the big square. The theorem we're going to use, the equation, would be shown like a squared for the small square plus b squared for the other small square equals the big square, or c squared. This is the equation that we're going to use for the whole rest of the chapter that we need to get pretty familiar with.